So now we turn ourselves to the global sensitivity analysis methods. In this session, I'll talk about Sobol method and regionalized sensitivity analysis. So global sensitivity analysis is really a desired tool in uncertainty quantification, simply because in very complex systems, it's poorly understood how combinations of input parameters actually lead to certain variations in responses. And so no longer can we rely on simple screening techniques or local sensitivity analysis. We would like to explore the entire space of uncertainty. The downside of all this is that this will lead then, of course, into greater computational costs. And so in that sense, later in the course, we'll also talk about emulators, proxy functions that allow you to speed up these calculations. The first method that I will cover is the variance-based sensitivity analysis, also called the Sobol method. So in the Sobol method is a variance-based method. So that means there's a total variation that we have in our something we'd like to response output. And we'd like to evaluate to what extent some input parameter contributes to that total variance. So evidently, if that input parameter does not contribute much, then that parameter is not very sensitive. Of course, the problem, of course, lies is when you have a lot of parameters, and in addition to that parameter have an effect, it could also be effect due to interactions between parameters. So in Sobol, we typically use two measures, which we'll introduce next. The first one is called the first order index. It's the contribution of that parameter without looking at any interaction. And then the total effect is, in addition to that contribution of that parameter, without interaction, we're now including also the interactions. So what is this Sobol index? So we'd like to understand what is the total variance of a response, how much that can be attributed to some parameter xn. In order to understand that, let's look at these two graphs here in the middle. So in this graph, we see x1 plotted versus y, and here we see x2 plotted versus y. So the conditional expectation of y given x is simply the regression you would make by simply, say, calculating within a certain interval what is the mean value. So we get this green curve here. And here we see that we have the variation of the conditional expectation of y given x2 is again the same function. So it's of course clear here that x2 is much more influential than x1. And the way we can understand that is by looking at the variation of this conditional expectation. So here we see that the variation of the conditional expectations over the range of y is substantial, while here that green curve seems to wobble just somewhere in the middle. So in other words, the conditional expectation of y given x1 is simply the conditional expectation of y. And so a measure, therefore, of sensitivity is to calculate the variance of that conditional expectation over the total variance of y. And that is the idea of calculating these Sobol indices. So in theory, we could say that any numerical computer model is basically a mapping of some input parameters on some output response. So here, for example, we see we have some input parameters, we have a computer model, and that returns us some scalar value y. So mathematically, we could say that any such function can be written in this form. And if you look at this form, we're not necessarily specifying what these functions are, but saying that this function can be written as a scalar plus a summing up of functions that are evaluated in each parameter. So this would then model essentially the effect of each individual parameter, plus when you have interaction, some other function that includes two parameters, and so on. The function includes three parameters until a function that includes all parameters. So under that circumstance, and essentially with an initial assumption of orthogonality of these functions, then we can write the variance of y, therefore, as the first term would now drop because the variance of a constant is simply 0. And then you have these individual varying terms. So these individual terms are then our conditional variances. So this would be what is the variance of the conditional expectation of y given each individual xn. We can also now look at conditioning on two variables. So we have essentially here the conditional expectation of y given any two of those variables. And so again, this would be a function that has some variation. So that variation, it goes into this term, and then accounting, of course, for the marginals of these variances, which are over here. So it also means that I can now look at the variation. You see that the variance of y is now described by a sum of different variances. There's a variance due to the effects of each parameters, but also variance due to the interaction of parameters. So it means that the total variance of this can be written as the variance of each of this individual component divided by the total variance of y. And that is essentially this conditional expectation. But we can go even further. We can also say there's an effect that is due to interaction. In other words, there's a variance due to interaction between any two parameters over the total variance. And so if this is zero or very small, it essentially means that there's very little interaction between those two parameters. And so interactions can go even to higher order interactions. We can look at 3 parameters at a time, 4 parameters at a time, 5 parameters at a time, etc. So the Sobol index or the Sobol method allows you to calculate all of these various interactions. So to summarize, simplify all that, we typically look at 2 Sobol indices. The first one is the green one that I showed you in the previous slide, is the first order Sobol index. So here we're looking only at the impact of parameter xn as terms of a partial variance. That means what's the contribution of variance to y of that individual parameter xn. In other words, another way of saying that is that saying this, how much is the variance of the response reduced if I would fix that parameter. If there's a large reduction, then parameter is considered very sensitive. Then there's also the total effect. So previously in this slide, I only looked at the contribution of that parameter Sn, but the parameter, that parameter Xn, but that parameter also is interacting with other parameters and contributes therefore, in addition to its single effect or its first order effect, it also contributes in that sense to the total variation of y by these interaction terms. And these are these various interaction terms that coming up. So I'm summing up over all those terms that are interacting with n. Okay, so it's a little theoretical. I'm going to go into the actual calculation of the Sobol index. That's quite complicated by itself. I'm only going to mention later on what the cost is of calculating the Sobol index in terms of computational cost. So let's turn to this case study first. So you have a case study of an oil reservoir. It's actually a case study modeled that was the Libyan reservoir in chapter 1 and chapter 8 of the book. And so we have various types of uncertainties. So typically in reservoirs, we have structural uncertainty, we have petrophysical uncertainty, we have fluid property uncertainty, etc. And so we end up with many uncertainties. So in the table here on the right, we list some of these uncertainties. All water contact is uncertainty. We don't know whether this fault is sealing or leaking or to what extent that's the case. We have fluid properties, and then we have geological properties, and even possibly numerical properties. So in this reservoir, we see that we have a number of injecting wells and a number of producing wells. And so the question is, in these producing wells now, is what is the oil, at some point we're going to get this water being injected, traveling to the producer, and we get water production in these wells. And that's, of course, something that's not desirable. So the question is, which of those parameters is most impacting the production at these wells in terms of water production? So the way we do that is just do Monte Carlo. We run many realizations, we do flow simulation, and we output the flow simulation here to various responses. So don't mind the colors yet, that come later, and we'll explain that. So here we have the water production in each well. So I have producer 1, producer 2, producer 3. I have the various production wells there, and we see this increase in water production. So we want to avoid this. So here we see that water production is delayed for a time here. However, there's a risk of having early water production. We'd like to understand what the impact of each of the various parameters are. So here we see that first order and total effect for the Sobol method. As I mentioned before, because we're calculating variances of conditional expectations, to calculate that variance with reasonable accuracy, we need a large number of flow simulations. Actually, you can calculate that amount. So for example, for 12 uncertain parameters, it will require 14,000 flow simulations. In addition here, of course, we have to do that for each time step. So what we notice, for example, is that because our responses vary over time, our sensitivities will vary over time. That means that parameters that are originally very important may after some time not be very important. And that makes sense, right? So as the model is, because the model is nonlinear, we should expect that there will be a changing around of importance of parameters. So here, for example, we notice that the oil-water contact, which is this parameter here, is a very important parameter, both in the single effect as well as the total effect. We also notice that that effect is going down over time, and as we produce the reservoir, then we see other parameters such as permeability and oil viscosity increasing. In terms of total effect, we see something relatively similar, except in the total effect we see the slight decrease and then increase over time. Okay, summarizing that, the variance-based sensitivity analysis is quite a powerful method for doing that. I think the sensitivity measure, even despite the fact that it's very difficult to calculate, it's a quite intuitive understanding in terms of proportional variance as it is attributed to each individual parameter. So in that sense, it has a lot to do also with what you may classically have learned in class about analysis of variance. There are some limitations, although those limitations are being worked at, that the responses typically must be univariate, that they're computational demanding, and so the use of surrogate models is being highly investigated in these kind of methods. Here we're now turning to the second method for global sensitivity analysis, which is called regional sensitivity analysis, and has some other variations. So again, we rely on Monte Carlo by generating multiple model realizations and performing some forward modeling, either the data response or the prediction response. So now the question is, how do we do sensitivity analysis with these data? So for example, here what we now start to focus on in this method, instead of focusing on variances, we're looking basically at something a little bit more rougher. For example, if you look at the responses here, we could say, well, there's some high responses, there's some medium responses, and there's some low responses. In other words, in general, if you have any response of any dimensionality, you can imagine clustering those responses into groups that reflect certain things. It doesn't have to be high, medium, low, but it could reflect any kind of feature of the response. So conceptually, that means that we could cluster some of these responses into groups, maybe 2 groups, maybe 3, 4, 5, 6 groups. And so if we do that, then in each group here, I have the red group, I have a response. That could be the high responses, and the blue group would be the low responses. But also with each point, which is a response, corresponds to a model parameter. And so in addition to that, we can look at the histogram of the model parameters in this group and the histogram of the model parameters in this group. And so logically, a parameter that's impacting or sensitive or influential is a parameter that has a different histogram in these groups. So take, for example, another simple example where I have 50 people shoot hoops of basketball, essentially, and score them. So you can imagine that if I take 2 groups of all those people and I put them in 2 groups, the people who scored low and the people who scored high, then I can look at properties of those people in each group. I may find that hair color is not important because the histogram of hair color in the good group and the histogram of hair color in the bad group is the same. But I may see, for example, that the height of that person may be influential, so that histogram would be different in those 2 groups. In other words, what we need to do is to simply make a CDF. So here, this is a CDF of the red group, the CDF of the blue group, and this is the CDF of both groups together. And what we notice is there's a difference in those CDFs. So this parameter is sensitive. So measure of sensitivity is therefore simply the difference between the frequency distribution of input parameter per each of these classes. And that's the basic idea of regionalized sensitivity analysis. To summarize that, an influential parameters will distinguish models into separate classes, and a non-influential will not do that. So for non-influential parameters, you would see that the distribution of that parameter within a class is exactly the same. Okay, let's now see how we can formulate that. And the way to do that, instead of looking at theory, let's look at a very simple example. Suppose that I have a computer model that has as input 3 parameters, x, y, z, and outputs something. And that something here is x plus y. So necessarily, I don't know that. Imagine that know that. I know only that there's a function. And I'd like to understand what is a sensitive parameter. Is it x, y, or z? And so obviously, in this example, we know that x is sensitive, y is sensitive, z is not sensitive, and the sensitivity of x and y are exactly the same. The problem, of course, I can here use the Sobol method, which gives me a very accurate sensitivity analysis. But imagine that the evaluation of this function takes a very long time. So I don't have that much time. I only have possibly 50 samples that I can generate. And suppose here that the prior distribution of XYZ is uniformly distributed. So the response here is simply a scalar, which I can group into 3 classes. It would go from 0 to 2. And I have the red group, the green group, and the blue group. So what I'm going to do is I'm going to look at the red group and see what the values of X are, what the values of Y are, and what the value of Z are. Do that for each group and compare that. Okay, so here is the prior distribution. So this is when I've done Monte Carlo, I look at the prior distribution of X, which of course is a uniform distribution. Then I look at the values of X in the blue group and the red group and the green group, and we see that particularly for the red group and the blue group, we see that there's a huge difference between the prior distribution, and that makes sense given that that parameter is of course a sensitive parameter. So I can do the same for Y and Z, and so for Y I get the same result, and for Z I get this result. Now, the problem is, of course, if you look at Z a little bit in greater detail, you may say, well, I'm not sure actually whether there's any kind of sensitivity or not. Maybe there is a sensitivity, or maybe it's just very small. And obviously, if you look at the example, the function x plus y, there shouldn't be any sensitivity. And the reason for that is that we get this somewhat separation here between these distributions is, of course, because I have a limited amount of samples. And so to account for this limited amount of samples and to figure out whether this difference is statistically significant, we'll have to do some kind of hypothesis test or Bootstrap-based hypothesis test. Okay, how does that work? So let's return to this our case where we have X and we see a sensitivity. So what we can do, of course, is calculate the area between those two curves, and that would be this number here. This is actually called the L1 norm, simply this area. And then we have the L1 norm for that class, etc. So we can fill this up, and we see big L1 norms, of course, for X, Y, Z, but small L1 norms for Z. Okay, so how do I verify that Z is indeed not sensitive? Well, we assume essentially that there's no, like the typical, such as the typical hypothesis testing idea is we assume there's no difference, and then we'd like to see, of course, to reject that hypothesis, the typical hypothetical deductive reasoning. So we assume there's no difference between classes. That means essentially that those distributions are exactly the same. And so what I can then do is if I can generate more samples from these initial distributions, what would be the typical variation that I would observe if I resample from these distributions? So that means that for each class, we're going to resample from the distribution, and assuming that essentially we have the uniform distribution in our particular case, we compute the distances between those distributions each time, and we get a different distance, and that then reflects the variation of our distance. Repeat that many times, and then we can calculate percentiles of that distribution. Okay, let's make that more pictorial. Suppose here that I have a case like this, and so what I have here in this one group, I have 13 samples, and as you say, well, is this parameter now really sensitive or not sensitive? The distance here is 0.051. Well, if I do Bootstrap, then I can regenerate more samples. So I draw samples from this black curve, essentially, and but I sample only 13, and so on. So now you see that this distance is changing, and so on. And I can make a histogram. So now what I could do is, what I can do here is look at this histogram and calculate, for example, a 95 percentile. What that means is that there's a 5% chance that despite the fact that I have no difference between the distributions, let me put up my pointer. So here we see that 95 percentile. There's a 5% chance that despite the fact that there is no difference in distribution, that this distance can be higher than this particular value. But you can see clearly, for example, if my distance was 0.3 or 0.2, like was shown in the previous case, then in the case of the X and the Y, then I would say that's sensitive. If I'm below that threshold, I would say that's not sensitive. So here, for example, this D is 2.87 is sensitive. Well, if you look at the Z, it would be somewhere in these 0.05 ranges, which is this essentially is. And so it is not sensitive. Okay, so how do I look at this information? So remember that I have essentially three classes. Remember, I had the red class, I had the green class, and the blue class. And so now what I do is I take my distance and I standardize it by the 95% percentile distance. Why do I do that? Because then, of course, if 95 percentile is my cutoff, then everything that's above 1 is considered sensitive, and anything that's below 1 is considered insensitive. And of course, there's some confidence related to that. We're going to go into that right now. So we can sum over all these distances over all these, average that out over these classes, and then make a single class for x, y, and z. And so here we see clearly x is sensitive, y is sensitive to the same extent, and z is not sensitive. So let's now turn to parameter interaction and how we will handle that in regionalized sensitivity analysis. So remember that interaction, we need to look at two parameters at a time and see how they are collaborating, interacting in order to create a response. In order to understand how interaction applies to this regional sensitivity analysis, let's look at the basketball example again. So we know, for example, that height is sensitive to scoring well on free throws. So you get a high score and low score for those that are taller. But what is the interaction with a person being left-handed or right-handed? Well, the way we can establish this out of our data set will be to look at those lefties, the left-handed people in the high-scoring group, and look at their distribution of height. What we'd like to understand now is how this different of the distribution height is in general distributed in the high-scoring group when we're looking at both left-handed and right-handed persons. And so we can ask the same question for the low-scoring group. So if these distributions are different, that means that there's an interaction between left-handed, right-handed, and the height of a person. You also notice that this interaction may be level dependent. That means that this interaction may happen for the right-handed persons, but not for the left-handed persons, or vice versa. We also need to be careful in including parameters that are dependent on each other. For example, if I would study height and weight, I will have a problem simply because height and weight tend to be correlated. So if height and weight are correlated, it's very difficult to interpret these interactions uniquely. Okay, so now we can formalize all that we said in the previous slide with some formulations in mathematics. So here we have, for example, the distribution of tall people in that class of, say, the medium or say the high-scoring group. So what we now look at is height left-handed people, where you have three classes: right-handed people, left-handed people, maybe bidextrous people, and see what their distribution is. And we notice now here, if I put my pointer around, we notice now there's a difference. And so that means there's an interaction between those two. So again, the way then to do that is via the L1 norm. So we're looking at the interaction. Now back to my example, x and y. So this is the function f of x comma y comma z is x plus y. Then here I look at what happens when y is small. That's y min. What is the variation of x in that group versus what is the variation of x in the medium group versus what's the variation of x in the maximum group, and what is also the variation in the group as in that group together, and so on. I can put that on there. I can put that on there. So then I have one bar. So now I can repeat that for all the classes. Remember, I have three classes in this x plus y example, and so I calculate these interactions. So similarly, we need to now know whether these are significantly different. So we do again a bootstrap, we standardize, and we get this particular result. So in this result, we see, for example, that x and y and x are interacting. That makes sense, right? X plus y is the function, but the interaction with z or any other thing with z is a non-negligible interaction, and that makes total sense. So there are many ways of plotting these results. As you noticed before, one way of plotting the result is simply to put my pointer on, is simply to look at all the three classes and look at the differences in L1 norms for those classes. So we sum that up, we can get something like this. And also, because we have a limited amount of samples, we can also look at some bootstrap confidence interval around these points. So for example, this is really very low, and so we'll never expect this to exceed that. But at some point here, in these bootstrap confidence actually put on the y-axis, then at some point you could say, well, these I'm getting less and less certain. This is probably not, maybe interacting, maybe sensitive or not, but these are clearly very sensitive. It's not really, I would say it's not really that important in the kind of context that we are doing this analysis, because we're really looking at these top hitters, whether this is marginally interacting, marginally sensitive or not. It's sort of not important, particularly here in case the oil-water contact is really the big hitter. Another way of plotting this, and this will also allow us to plot interactions at the same time, is to again look at the percentiles. So remember that we're doing this bootstrap idea where we generate an entire histogram of these distances, and then we say something that is sensitive when it is essentially it lies on the right hand side of this 95% line. So this 95% line is just a choice. So what we also simply can plot is if I have a value of 0.25, I can plot essentially what is the percentile. And so the percentile will be very high here, we both close to 100%. Well, if my d falls over here, for example, a parameter is not sensitive, then that percentile will be very small. And that's what we see over here. So here what we're plotting is we see our 95 again. And so we notice here that this is essentially probably some distance that was very high. So this is certainly critical or important. These are important, these are insensitive or not critical. So we can do the same thing for interactions. So here we see, for example, in the DNAPL case, contaminant case involving that river, that we are plotting the main effects. So this would be the effects here. That was on the previous slide. So what we can then also do is look at the interaction effects and look at the essentially the percentile for the interacting effects. So what we're doing there is we're making this nice little matrix. In this matrix, we have basically the parameters. So we see these parameters. I've also ranked the parameters from in terms of their main effect. So this is main effect is high. And then on the diagonal here, what you get are these values. So for example, 23.5 is this value here. 87.6 is this value here. And next to that, I can also look at interactions. And this is an interesting plot. What we, for example, see is that there's these high parameters, and then we have less parameters, and then we have less important parameters, and we have insensitive parameters. But there are some of these insensitive parameters that are interacting with the big parameter. So that's an important thing you have to understand. Just removing this from the analysis is going to have an effect because its effect of the interaction is being removed. And so this matrix is really nice to understand the problem that you're facing. So if there's a lot of off-diagonal elements, that means that the problem is highly nonlinear, and so we have to be very careful in removing certain parameters or fixing parameters to certain values. So this idea of the RSA that I just explained is also called distance-based generalized sensitivity or global sensitivity analysis. It's distance-based because you were looking at the L1 norm between distributions, for example, distributions of the total of the class versus conditional distributions of parameters in that class. That's why we call that distance-based sensitivity analysis. The other thing, the reason why we use distance-based is because we can use the distances essentially to classify the responses in certain classes. So that distance can be used. We can go into multidimensional scaling, and so essentially there's a good combination between multidimensional scaling and distance-based generalized sensitivity analysis, particularly when your response functions are high dimensional. So if you apply the DGSA to the Libya reservoir case, remember it's the same case where we applied the Sobol methods, and we'll find this this plot on the left here. So these are just the main effects, so that should be compared to the first order effect in Sobol. And so what we notice is that we get very similar results, is that we get all water contact seems to be important. And then what we get is the other parameters are less important. So we notice that the lines are less smoother, and that's also, of course, because, of course, we do less flow simulations. So DGSA, it gives a little bit of a rougher idea of sensitivity, but in most of the applications we're thinking about, we really don't care much about the fine-tuning of these very non-important parameters. And so if you then really want to understand in great detail, then you can potentially run Sobol, but that requires running many more flow simulations. Okay, that sums that up. So here are some takeaways for pros and cons for distance-based generalized sensitivity analysis.